Okay, anybody have any homework questions from last time? Okay, so last time I brought up the idea of a rotation matrix. So I'm going to do an example where where that comes up at the end. Um, and it's also just an example of a particle statics problem. Yeah. Oh, okay. You just had the right question. Okay. So let's say that we have an incline and an angle of 30 degrees um, and a friction contact between the incline and a 10 kilogram box. Um, and we want to calculate, so like all our problems, this is in static equilibrium. Um, and first we want to calculate the force on the box by the incline. And second, we want to calculate, so we'll break up that force into normal and friction components. So basically all I'm doing here is in statics, we don't care how that force breaks up into a normal force and a friction force, but I just want to try to reinforce the idea that they are the same thing. We're just not thinking about them that way. And then also I just want to show you this rotation matrix in action for the first time. So first I'm going to draw a free body diagram of the box. We have a weight force down of 10 times 9.81. And then this is a friction contact on the box. So I'm going to draw my coordinate axes like this, and I'll just call that F. And what we want to calculate is that F. Now, go around the boundary. There's no other place the surroundings contact the boundary. So we know this free body diagram is done. And now we can go to Newton's second law. And it says that 0, negative 98.1 plus Fx, Fy is equal to zeros. And so Fx is equal to 0, Fy is equal to 98.1. And in other words, this force vector acting on the box from the incline is 0, positive 98.1. Okay. So that is, so F is the sum of the normal force and the friction force. It's just not apparent because of our coordinate system. Yep. Right. Yes, exactly. So So in physics 1, you would have done this problem with, so we did this calculation with our coordinate system like this. We didn't mess with it at all. In physics 1, you did this calculation always with a coordinate system with the x-axis along the incline and the y-axis out of the incline. So now we're going to use a rotation matrix to come up with the answer you would have gotten in physics 1. Okay, so so now we're going to re-express this vector in a coordinate system that's oriented like this. Okay, so in order to do that, first we have to figure out this angle theta. So we're going from, so this is the coordinate system where the vector is originally defined. And we're going to this coordinate system. And counterclockwise, how do you have to rotate the one on the left to make it line up with the one on the right? Yep, positive 30. If it was clockwise, then it would be negative, but this is, yep. And by the way, I would put your calculators, the mode on your calculators, do it in degrees. I'm going to do all my angles in degrees. So, okay, and now we can say that the rotation matrix is cosine of 30, sine of 30, negative sine of 30, cosine of 30.
The Q means rotational matrix?
Yeah. And that's a Q for some type of, I can't remember what the class of matrices is. There's a reason that it's called Q, but I don't remember what it is. But I'm always going to use Q for rotation matrices. The little squiggle says it's a matrix, the same way as an arrow over the top says something's a vector. So we got 0.866, 0.5, negative 0.5, positive 0.866. And now our, yep.
Why the cosine, the sine switches from a positive to negative on the bottom, but the cosine doesn't?
Yeah, really the most useful answer to you is that's just a formula and just use it that way.
So
but
angle we're changing it to, be it -2 or,
right.
Put that into the...
Yeah, it's always cosine sine, negative sine cosine, and just put in whatever angle, exactly. And so F nu now is going to be this 0.866, 0.5, negative 0.5, 0.866. And we're going to multiply it by the force vector in our old coordinate system. And the way you calculate matrices, well, first of all, you don't ever have to do matrix multiplications. You don't have to know how it works. Your calculator will do it for you. Just use the regular multiplication sign. Yep. Because that was our vector in the original coordinate system. So you're always, I think at the end of last time I said, so it's always going to be this rotation matrix times the vector in the old coordinate system is equal to the vector in the new coordinate system. And so the way this works is 0.866 times 0 plus 0.5 times 98.1. And then for the y component, negative 0.5 times 0 plus 0.866 times 98.1. And what you get is negative 49.05 for the x component. And
I got positive.
yeah, everything's positive, isn't it? You're right.
And we can check that because we know what quadrant it would be in.
That's true. Yep. And 84.95.
96. We're rounding.
Okay, yeah. I'm going to leave it. And this is the normal force. And this is the friction force. Any questions about that?
The x component is gonna be always the friction force.
Well, in this case, yeah, because the friction force is always going to be along your rotated x-axis. Because, you know, you orient the coordinate system with the x-axis along the incline. Yep. Okay, let's do another example. This one relates to pulley advantage. Maybe you've seen this in Physics 1, but I remember when I first took physics, the first time I saw pulleys, I had heard before that pulleys had this way of letting you support big weights by applying small forces. And so I was confused when I first saw that all a pulley does is change the direction of like a cable force. Like a pulley on its own doesn't do anything to reduce the force required to lift something. But you can configure pulleys in a way that they do require less force to lift something. So let me do an example where you see that. So here is a ceiling. And let's say that there's a pulley attached to the ceiling there. And then there is a hanging pulley that's attached to a mass. So this has a mass of 10 kilograms, and a cable goes over the one attached to the ceiling, under the hanging one, and then connects to the ceiling. And if I set this up, so what we're going to calculate is this force T. Okay? And yes,
That force T is just going like straight.
it can go any angle if the if that's a rigid support, but you could think of it as going down. Okay, so if all we had was, so if there wasn't this hanging pulley here, there was only a pulley attached to the ceiling, and you just had 10 kilograms attached to one side of a rope, and the rope went over, and then you were holding the other side. That T would be equal to the weight of the mass. So that T would be 98.1. Okay, but what we're going to see is with this setup, to keep it in static equilibrium, that T is half of the weight. It's going to be 49.05. Okay. All right, and so the first question always in doing a static problem is what you're going to choose as your free body. Like, what are you going to isolate? And you can isolate anything that you can put an imaginary like shrink wrap around. Okay, anything that you can have a closed outline to can be chosen as your body. That's why we draw free body diagrams always as a closed outline instead of like a stick figure or something. Yes.
For the representation matrix, will that be provided on tests or do we?
Yeah, I don't think I'll ever put that on a test.
So we would either. Okay,
Yeah.
So we don't. Do we need to memorize it?
No. So the thing that we're going to isolate as our free body is I'm going to isolate everything that's hanging. So the hanging pulley, the mass, and just to be kind of clear on what's going on, I'm going to choose a little bit of this cable too. So it's all of that cable that's going underneath the pulley and all of that. Okay? And now I'm going to draw my free body diagram of the system. And so I'm going to, this is just an outline. So there's the little pieces of the cable that are included. We're including all the cable underneath, and we're including the mass. The weight of this system is 10 times 9.81, so 98.1. And now we're going to go around the boundary looking for contact with the surroundings. The only two places that the surroundings contact the boundary is where part of the cable touches the other part of the cable. And so it's pretty clear that that's going to be a pulling force. And since it's the same cable, it's going to be the same pulling force in both cases. Any questions about that? And now we'll go to Newton's second law. And we have 0t plus 0t plus 0 negative 98.1 is equal to 0, 0. So the y equation says 2t minus 98.1 is equal to 0. And t is equal to 49.05.
Can you go up a little bit?
Yeah. Something feels a little fishy. A question?
With pulleys, can you just assume every time you add a pulley that you take another like 50% of the?
Yeah. Let's see. So every new hanging pulley you put in
Splits it in half again?
gives you 2 more t's that you're dividing that force by.
Okay.
So if you have another hanging pulley, then it's going to be this divided by 4. Another one, it's going to be this divided by 6, by 8, 10. Although I'm going to do one example quick where we see that for this to work, it's required that those cables are vertical. And as you start to lift this thing, those cables, well, that's not true, but they do have to be vertical. So if you have this thing spread out with this is over here and there's an angle on those cables, you get very different results. I was going to say, it feels like you're breaking some law of the universe, like something doesn't feel quite right about this. And you do have, if you think of it in terms of energy, so we're just thinking about it in statics. So the thing is just at rest and there's no energy issues at all because there's no work being done because nothing's moving. But if you start using this system to lift this thing up, you can't get an amount of energy without putting that same amount of energy into it. And so how is it that as you pull this rope with 49.05 Newton, you're lifting this weight of 98.1 Newtons? You know, does that violate conservation of energy? Yeah.
You're doing half the weight, but the rope is twice as long.
That's perfectly, yeah, that's exactly right. So you do get to have a lighter weight. It's like gearing down on your bicycle, basically. You do get a lighter weight, but you have to pull the rope twice as far to raise this thing half as high, you know. Okay, let me do one at an angle. So let's say this time we have a pulley there, a hanging pulley here. Let's make this 10 kilograms again so it's easy to compare. But this time the cable goes like this. I gotta make this longer. And this. And let's say that these angles are 20 degrees. Okay, so in this case, what's that force T that you have to apply to hold this up? So I'm going to choose my free body diagram the same way, my free body the same way. So the free body diagram looks like this. We have the weight of 98.1 and the forces P and T. But now when we go to Newton's second law, we have to use cosine and sine to represent the directions of those. So we have the force over here that's equal to T times the cosine of 160, T times the sine of 160. The one on the right is T times the cosine of 20, T times the sine of 20. Then plus the weight force of 0, negative 98.1. This is equal to zeros. Plug in those sines and cosines, and you get negative 0.940 T, positive 0.342 T, plus 0.940 T, 0.342 T, plus 0, negative 98.1 is equal to zeros. The x equation, these two things cancel, so the x equation doesn't give you anything. The y equation says 0.684 T is equal to 98.1. Can someone divide that for me? What do you get for T there? So it's going to be something bigger than half.
43.4.
143.4. Okay. So it's still decreasing the force that you need to apply to hold it up. Oh, 143.
Yeah. Should,
I also got 143.42.
Dividing 98 by
Right.
something smaller than
Right.
1.
Yeah. So in this case, because that angle is shallow, that angle is just 20 degrees from the horizontal, it's actually taking more work to lift this thing than if I didn't draw a picture of it, but if you just had it hanging over a single pulley. And as that angle gets closer and closer to horizontal, that tension required to hold that thing up approaches infinity. So don't build one of these things with those cables horizontal. Yep.
What angle does it start getting easier to lift it?
At what angle does it start getting easier to lift it? So I guess that is when 2 times the sine is equal to 1. So 30 degrees, I guess. At 30 degrees, it's exactly the same as just a single pulley. Okay, so that's it for rigid body statics. And now we're, for particle statics. And now we're going to get into rigid body statics, which is like the big topic in this class. Okay, so in rigid body statics, the equations of motion bless you, are going to be, so first Newton's second law, that's the one that we had in particle statics. And if you're doing 2D problems, Newton's second law gives you 2 equations. And if you're doing 3D problems, Newton's second law gives you 3 equations. But with rigid body statics, we're going to add a new thing, which is the moment equations. So Newton's second law, let me write this too. So Newton's second law for statics says that add up all the forces, they have to be equal to 0. Now we're also going to use the moment equation that I'll abbreviate as rotational Newton's second law because you derive it from Newton's second law. And it says that if you add up all the moments about some point A, it has to be equal to 0. In 2D, this gives one more equation. And in 3D, this gives 3 equations. So altogether for rigid body statics, in 2D, you have a total of 3 equations. And in 3D, you have a total of 6 equations. One thing I want you to notice here, I said this about calculating tensions in cables, that doing statics before dynamics can give you sort of some bad habits sometimes. In statics, the tension in a cable is just equal to something that's hanging from it. In dynamics, that's not true. Here's another big one where we're going to get some habits here that do not apply when you get to dynamics. So this is a bad habit alert.
Quickly,
Yeah, I will. That's the next big thing I'm going to get into. So, and that is in statics. The about point A can be any point. Even points that aren't on the body. In dynamics, there are only two acceptable about points. The first one is the center of mass of the body. And second is a point on the body that's fixed in your coordinate system. Let me say this is a material point on the body. So like, for example, a point that's fixed in your coordinate system would be like if you have a bar that's connected to the floor by a hinge, then that hinge is a point that's connected to your body, and it also is fixed in the coordinate system as this thing moves. Okay, so we're going to get into this habit for this entire class where you can put your about point anywhere that makes sense to you, on the body, off of the body, but when you get to dynamics, that's not going to work anymore. Okay? So now, the first step we need is to define what a moment is. So a moment, and people call it a moment. What it really is the moment of a force about a point. In physics, you probably use the term moment and torque interchangeably. In engineering, we use torque to mean a specific combination of moments, and so we're going to use this word moment instead of torque. For physicists, they tend to use them interchangeably because they don't deal with anything specific. They don't have to worry about stuff like that, you know. And so here is just the arbitrary body that we're going to be talking about. And at the point P, there's a force. So let me just say, okay, at this point P, which you can think of, remember that, so P is just coordinates, but you can always think of coordinates as vector components. So that's why even though P represents coordinates, I'm thinking of it as a vector that goes from the coordinate system origin to the point. Question?
So a moment is like it's the force on a single point at a single instant?
No, but let me define what it is. And so we have a force F acting at P. Hold on a second. So let's say this is our force F. And then we're also going to choose an about point A. And so I'm going to just arbitrarily put it over here. And again, I'm going to think of those coordinates as vector components. And then I'm going to define a vector that goes from A to P. And I'm going to call this vector rho. And so if you wanted to calculate the components of that vector rho, you would do that by taking the coordinates of P and subtracting the coordinates of A. So A is the coordinates of the about point. P is the coordinates where the force is applied. And then with those definitions, the moment of that force F about A is a vector that's equal to rho crossed with F. If you're doing this calculation in the plane, which is most of the stuff we're going to do is just going to be plane problems, well, that rho vector and F are both going to be just X and Y components. So when you take the cross products, you're only going to get a Z component. Okay. Notice that that moment always has to be perpendicular to both rho and F.
The vector if it's a coordinate.
Well, coordinates, you can always think of coordinates as a vector from the origin to the point. Yep, so coordinates are equivalent to vector components. So intuitively, here's what a moment is. Like if you're trying to turn a bolt that's stuck with a wrench. So you're going to apply a force like this. The about point is over here. This is P. And so the rho vector goes 2P from A. And there's two things you can do to turn this stuck bolt. One is wherever you apply the force the first time and it didn't work, you can apply a bigger force, right? That can make it turn. Or the other thing you can do is move from the point where you applied the force the first time farther away from the, use a bigger wrench or something. Both of those two things contribute to the torque, the moment that you produce. Okay, so that's what a moment is kind of intuitively. It's not a force. It has its own units of Newton times meters, or like if you use torque wrenches or something, maybe you use foot-pounds or whatever. But it's always a unit of a force times a unit of length. And it tells you the tendency that a force has to produce a rotation in an object. Okay.
So if you have 20 degrees to counterclockwise, would that increase the moment?
If you moved F 20 degrees counterclockwise, Well, so, but the wrench is the same.
Yeah.
Okay, but you change the angle of the force? Okay, remember that cross products, the absolute value of the cross product is biggest when the two vectors are perpendicular to each other.
Okay.
So this is the biggest, that's the direction, the optimal direction for applying that force to turn this
So
body.
to make it bigger, you get a longer wrench, or what was the other one?
Apply a bigger force, bigger magnitude of force.
Relative to the, build, it's still the same, if you were to analyze what the bolt was doing in terms of force or motion, you apply greater force or went at greater distance away before turning the wrench?
Yeah.
It'll just be the same, like, I will be able to tell the difference from that.
Right. Yeah. I mean, the thing that induces the rotation is the moment. And if you double that force or double that distance, those have the same effect on the wrench. Yep. When I do calculations of moments, I'm going to always put them into a table that just I find very useful for organizing this stuff. And so my table is going to look like this. There's going to be a column for the row vector, a column for the force, and a column for the moment. And for a single body, just like when you use Newton's second law, we're going to calculate the moments produced by each one of these forces. So we're going to have force 1 is going to have some row vector, whatever it is, 0.5, negative 2.5, 3.0. The force is going to be, let's say, 0, negative 200, positive 450. And once you have those for force 1, then you can calculate the cross product. I did not think this through. Ooh, but I have my calculator here. So cross product. So 0.5, negative 2.5, 3, with 0, negative 200, 450, gives a moment of negative 525, negative 225, negative 100. And then you'd go on and have another row for the next force, and on until you've gone through all the forces that appear in the free body diagram. Okay. Anyone have any idea, just to Newton meters, even people who work with torques a lot probably don't have a very good sense of how big a Newton meter is. Anyone have an idea how, say a screwdriver, how many Newton meters of torque could you apply with a screwdriver to something? Somewhere around 10. So if you're really cranking on something, 10 Newton meters. Okay. So ones in the hundreds are pretty big. Ones in the thousands are huge compared to our experience. All right, let me do one. Do I have time for this? Let's try. I'll stop if we run out of time. So let's do an example. I'm going to give you a free body diagram, and we're just going to fill out the table and calculate the total moment. So the free body diagram looks like this. We have an unknown force R down here. A weight force of 500 newtons from the center. A normal force that's unknown there. and then a force of 80 newtons. I guess I'm not putting the units in, but it's in newtons, and let's say that this is 60 degrees. And if this is in static equilibrium, we want to calculate what R and N have to be. Well, we can choose our about point anywhere we want, but it has to be consistent once we choose it for one of these forces. So I don't know, I'm going to choose my about point here. Right where that R force is. Wherever you choose the about point, the force that's at that location is going to produce 0 moment. So sometimes you can simplify your calculations that way. And let's write out the table. So we have rho, force, moment. The first force I'm going to deal with is that R. What's the rho vector that goes from the about point to where the force is applied? 0, yep. So we got 0, 0, 0 for rho. The force is Rx, Ry, 0. Cross product is 0. Then we'll go to the 500 Newton force. Oh, I didn't give any dimensions. Let's pretend I did, though. Let's say this is 1 meter, and this is half a meter. So the rho vector that goes from the about point to where the force is applied is 0.25 in the positive x, 0.5 in the positive y, and then 0 for z. The force is 0, negative 500, 0. And the cross product is negative, it's 0, 0 for x and y, and then negative 125 for z. I'll just fill out this table and then we'll stop. And then we have that normal force. The rho vector from the about point to where that normal force is applied is 0.50. The force is 0, n, 0. And the cross product is 0, 0, 0.5 n. And now the last one is that cable force, the 80. From the about point to where that force is applied is 0.5 in the x direction, 1 in the y direction. Hi, I'll be out in a sec. So we got, let's see, I'll just do this trigonometry. We got 80 times, so we have 40,
80 times what?
80 times cosine and sine of 300. So 40, negative 69.282, 0. And the cross product is 0, 0, negative 74.641. Okay, so what we have now with this table is we have all of our forces here, and we can add those up for Newton's second law. And we have all of our moments here, and we can add those up for rotational Newton's second law. What? The row vector. That row vector is just the vector from the about point to where the force is applied.
So like if you're just pulling